Namaste, welcome to the channel. Today we will discuss the topic of ideal and non-ideal solutions. So let us first discuss what are ideal solutions. Ideal solutions are those which obeys the Raoult's law at every condition of temperature and concentration. So ideal solutions are those solutions which obeys Raoult's law, at every temperature and concentration. At every temperature and concentration, when the solution obeys Raoult's law, the solution is called as ideal solution. Okay, so in case of ideal solution, the change in enthalpy and change in volume after mixing remains equal to 0. It remains equal to 0. What does this means? That when you are mixing two components in a solution, then the heat change is 0. Heat change is 0. This means that delta H value is equal to 0. And when you are mixing two different types of component in the solution, then delta V mixing is 0. Delta V mixing is 0 means that the change in volume after mixing the two components will be equal to 0. There will be no increase in volume and also there will be no decrease in volume. So delta V after mixing remains equal to 0. So let us take an example first. Suppose you are mixing 50 centimeter cube of benzene, 50 centimeter cube of benzene with 50 centimeter cube of toluene. We take the example of 50 centimeter cube of benzene means 50 ml of benzene you have mixed with 50 ml of toluene, then the volume of the solution after mixing will be equal to 100. It will be equal to 100 centimeter cube after mixing. So the delta V after mixing will be equal to 0. This means the solution is behaving according to Raoult's law, and it is called as ideal solution, and there will be no change in heat energy. This means there will be neither endothermic reaction nor it will be an exothermic reaction. Okay, no endothermic and exothermic reaction will be there in case of ideal solution, because delta H mixing is equal to 0. So in case of ideal solution, what actually happens if we take a binary solution having two components A and P, then the intermolecular interactions between the two components A and B after mixing, they are equal to the individual interactions present in the solution for different components. This means the new interaction which is formed between the two components and the individual interactions present in the two components, it is equal in both the cases. Okay, so can we say that the ideal solution, in case of ideal solution, intermolecular interactions between AB are of the same magnitude as that of AA interaction and as well as of BB interaction. Okay, AB interactions are same in magnitude as equal to AA interaction or BB interaction. But actually or practically we have no ideal solutions. No ideal solution is found actually or practically. But if the concentration of the solution is low, if we take the concentration of the solution as low concentration or dilute solution, then what will happen? The solution will behave as an ideal solution. In case of low concentration or dilute solution, the solution will behave as an ideal solution. Okay, and practically there are no ideal solution. But in case of low concentration or dilute solution, the solution behaves as ideal solution. See, one example we have already seen here, that benzene and toluene together mix to form ideal solution. Take second example. You can take the example of N-hexane and N-heptane. They both together combine to form an ideal solution, or you can take the example of ethyl chloride with ethyl bromide. Ethyl chloride with ethyl bromide. So these are the examples of ideal solutions. Chlorobenzene with bromobenzene. You can also take this example in case of ideal solution, where delta V mixing is equal to 0 and delta H mixing is also equal to 0. Now we will see the another type of solutions. If the solution is not behaving as an ideal solution, then it will behave as a non-ideal solution. Simple. It will behave as a non-ideal solution. So what are the non-ideal solutions? In which the delta V mixing, that is when you will mix the two or more components in the solution, then it is not equal to 0. There will be a change in volume. There will be an expansion or contraction of the volume after mixing. Or we can say that delta H after mixing will not be equal to 0. Okay, so the reaction may be endothermic or exothermic. Take the example of non-ideal solution. In case of H2SO4 with water, when you mix the two components H2SO4, sulfuric acid and water, then what happens? Large amount of heat is released and there will also be a change in volume. Okay, when you mix sulfuric acid and water together, then large amount of heat is released. When large amount of heat is released, this means that delta H after mixing will not be equal to 0, because now it is an exothermic reaction. After mixing, the reaction has become exothermic. So the delta H mixing is not equal to 0. And see, in case of non-ideal solution, what happens? That we were talking about Raoult's law, how the solutions behave for Raoult's law. So let us discuss this with a graph in which we are plotting the graph for vapor pressure and mole fraction. We are plotting here the graph for vapor pressure and mole fraction. Vapor pressure and mole fraction. So when we draw the graph for vapor pressure and mole fraction, in case of two components, suppose we are taking here component A mole fraction, which is equal to 0, and slowly we are take it as unity. Okay, and slowly we are adding another component mole fraction in it, but at this point mole fraction due to B component is equal to 0, but we are increasing here the component B in the solution, and at this point the mole fraction of component A will become equal to 0, and the mole fraction due to component B will become equal to unity. So the vapor pressure at this point where the mole fraction is equal to unity will give the vapor pressure due to pure component A. Okay. Here we will get the vapor pressure due to pure component A, which is represented here by PA naught. Here it is only because of the component A. The vapor pressure is only because of component A, and we will represent here by PA naught. And at this point the vapor pressure is only due to the component B, because these are two different components. So the vapor pressure of individual pure components will be different, and we are showing it by plotting at a distance. Now meet these 2 points together. Okay, meet these 2 points together. So in case of Raoult's law, the vapor pressure of component A becomes equal to mole fraction of component A into vapor pressure of pure component A. And in case of pressure due to component B is equal to mole fraction of component B into vapor pressure due to component B. Okay, in case of only Raoult's law. And Raoult's law is which solution is showing Raoult's law behavior? Ideal solution. And here we will taking the example of non-ideal solution. In case of non-ideal solution, either they will show the behavior which causes the positive deviation from the Raoult's law or the negative deviation from the Raoult's law. either they will show the positive deviation from the Raoult's law. Positive deviation from Raoult's law. What does this means? How the solutions show positive deviation from Raoult's law? So in this case, what happens exactly that the pressure due to B component, pressure due to B component becomes higher than the expected Raoult's law behavior. Similarly, pressure due to A components becomes higher than expected from Raoult's law behavior, and the total vapor pressure of the solution also becomes higher than expected from Raoult's law behavior. Okay, the total vapor pressure here for Raoult's law will be equal to PA plus PB. P total is equal to PA plus PB in case of Raoult's law. So, what is the positive deviation from Raoult's law? When the vapor pressure shown by the individual components and the total vapor pressure of the solution is more, or the line is going above than the expected Raoult's law behavior. It is called as positive deviation from Raoult's law. Why does it happens? It happens because when we take the kind of solutions in which there are strong intermolecular forces of attraction. Suppose we are taking the example of ethanol. In case of ethanol, see, in case of ethanol, there is a hydrogen bonding between one molecule of ethanol and another molecule of ethanol. So, the molecules are tightly held because of hydrogen bonding present between ethanol molecule. But if we try to induce here the another component, suppose we are adding here, we can add here cyclohexane or acetone to make a solution. We are adding acetone or cyclohexane, then it will break the hydrogen bonding which is already present in the ethanol molecule to form a solution. Acetone molecule will break up the hydrogen bond which is already existing between the ethanol molecule to form a solution. And in this case, what will happen that the individual pressures of the component will become higher because now they are more available to get into the vapor state easily, because there are no intermolecular forces of interaction present in the individual molecules. So, they are easy to evaporate. They will show higher vapor pressure. See, in case of this is pressure due to PB, this is pressure due to PB, and this one is due to PA, and this is the total vapor pressure of the solution. Total vapor pressure of the solution in case of non-ideal solution, which shows the positive deviation from the Raoult's law. So, what is happening here? Because the individual interaction has broken. When you are introducing a new molecule which breaks the intermolecular force of interaction with that was already present earlier in the individual component, then the solution which will be formed after mixing the two component will show a positive deviation from the Raoult's law, because there are no interaction. It is easy to get evaporated. The vapor pressure will rise, and we know that vapor pressure is inversely proportional to boiling point. Vapor pressure is inversely proportional to boiling point. More will be the vapor pressure, lower will be the boiling point. So, the solutions which show the positive deviation from the Raoult's law behavior will act as minimum boiling azeotropic mixtures. They act as minimum boiling azeotropic mixtures. Minimum boiling azeotropes. Now, what are azeotropes? Azeotropes means there is a solution that boils without showing any decomposition. Okay, so they distills without showing any change in its composition. What are azeotropes? Azeotropes are the liquid mixtures which distills, means which boils without change in composition. Without change in composition. they are called as azeotrophs or constant boiling or constant boiling mixture. Okay, so here in this case, the azeotropic mixture will be minimum boiling azeotropic mixture. Minimum boiling azeotropic mixture will be formed in case of solutions showing positive deviation from the ideal behavior. Okay, so this is the example of positive deviation showing solutions from Raoult's law behavior. But in case of another kind of solutions in which there is the negative deviation from Raoult law, there are solutions which show negative deviation from the Raoult's law behavior. And what are these kind of the solutions? See, what is the difference between the positive and negative deviation showing solutions from Raoult's law behavior? The line is running below the Raoult's law behavior in case of negative deviation showing Raoult's law. Okay, so here let us take one example. Which solutions show the negative deviation from the Raoult's law behavior? Negative deviation from Raoult's law behavior. So in this case, suppose we are taking the example of chloroform CHCl3 with acetone. Chloroform with acetone. Then what happens here? If we take this example, then suppose in case of chloroform, it can form hydrogen bond with acetone. It can form hydrogen bond with acetone. So in this case, a new force of interaction, that is hydrogen bonding, is formed after mixing the two components in the solution. And when the new interaction is formed, then what happen? Vapor pressure will decrease and boiling point will increase. So we'll get the maximum boiling azeotropic mixture. We will get maximum boiling azeotropic mixture here. Maximum boiling azeotropic mixture here. When vapor pressure decreases, boiling point will increase because they are inversely proportional. Why the vapor pressure is decreasing? Because there is a new force of interaction which is formed after mixing the two components. This will decrease the vapor pressure of individual component in the solution, and so the boiling point of the mixture will rise, which will give the maximum boiling azeotropic mixture in case of the solution showing negative deviation from Raoult's law behavior. Okay. So this is the example of negative deviation showing Raoult's law behavior. What is the main differences between the two types of the solution according to their equations? So in case of negative deviation showing Raoult's law behavior, PA, value of PA, it is less than the mole fraction of A and P naught A. In case of negative deviation, PB is also less than XB into P naught B, and therefore P total will also be less than the sum of these two values, XA into P naught A plus XB into P naught B. This is the equation for the solution showing negative deviation from the Raoult's law behavior. Okay, we have discussed the graphical behavior and the equations related from the two solutions showing negative and positive behavior. And also in case of negative deviation from Raoult's law, if there is a formation of hydrogen bond or dipole-dipole interaction, then actually what will happen here, the delta V mixing, it will not be equal to 0, and delta H mixing will also not be equal to 0. In fact, it will show the positive value. Okay, it will show the positive value. So delta V mixing will be equal to positive, and delta H mixing will also be equal to positive in case of negative deviation from Raoult's law behavior. But in case of the solutions which show positive deviation from Raoult's law behavior, what will happen here? Delta H mixing, when we mix the two solutions together, it will be equal to negative. It will not be equal to 0 and it will be equal to negative. Delta V mixing will be equal to negative. Delta V mixing will be equal to negative. This means that there will be the contraction in the volume. Okay, and delta H mixing is also equal to negative. So the interaction between the components are greater than the pure component. In case of negative solution and in case of positive deviation from Raoult's law, the interaction between the components are less than the pure components. So this is the topic for today, and we have discussed ideal and non-ideal solutions with examples, equations, and the necessary conditions. Okay, hope this will help you. Thank you.